Hey, so we are now into our new chapter, which is reactions in aqueous solutions, our new unit. Okay, so this unit we're talking about where we have solutions and reactions are taking place. So I got two solutions here, right? They are just look clear, they just kind of look like water, but really this is lead iodide. It's got a bunch of potassium and iodine atoms floating around there, or ions. And this is lead nitrate, so there's a bunch of lead and nitrate in there, but you can't really tell, right? They just look like clear liquids, but there are some ions floating around there because they're dissolved in water. And then what we're going to be focusing on is when these things react, what happens afterwards, right? Now we got some sort of precipitate in there, okay? We have some sort of solid that has formed that's yellow, okay? We're going to be talking about that and what's happening with these types of reactions that involve aqueous solutions. So, first things first is that we have to talk about some definitions. And I forgot my marker, so I gotta go get it. So, these definitions, starting out, first of all, is solute, okay, which is just your solids being dissolved. Okay, you guys might remember this from last year. It's your solid being dissolved as your solute, right? So if I got a beaker of H2O and I'm putting some salt in there to be dissolved, that NaCl, that solid, is your solute. Okay, and then there is solvent, which is the substance doing the dissolving. Which in this case, my example, right, is the H2O. The H2O is dissolving that NaCl, okay, and then you have the solution.
Hey everyone, I hope you all had a great.
So anyway, the solution is the mixture of the solute and the solvent, okay? So I'll say mixture of solute and solvent. Okay, so once we put that NaCl in that water and it dissolves, okay, it's no longer NaCl in that water, it's a bunch of Na ions and chlorine ions floating around. They break apart and they're in their ions and they're able to chill in there because they're dissolved and they're staying balanced and not reacting because that water's in the way keeping them dissolved, okay? So we have solute, solid being dissolved, solvent, liquid doing the dissolving, and solution is the mixture between the two, solute and solvent. Okay, solution is the one you're going to be hearing the most. And then it's time for a word that you've probably heard a lot, thanks to Gatorade, and that is electrolytes. Okay, electrolytes, right? Gatorade is an electrolyte, and all that is, it's a aqueous solution that conducts electric current. Alright, so it's just a liquid that conducts electric current, okay? A strong electrolyte is salt water, okay? It conducts electric current. A weak electrolyte is pure water. It doesn't conduct electric current, okay? So if you took pure water and put, I've said this before, put a toaster in it, you wouldn't get electrocuted, okay? It's just that when most people get electrocuted in water, the normal water we use from like the tap has a bunch of iron in it, it has calcium in it, okay? There's a bunch of other dirt and stuff floating in there, so it's able to conduct electricity. So what's the difference? What makes something a strong electrolyte, okay? It's just the ions that are in it. When I look at H2O, pure H2O, it's just got a bunch of water molecules floating around, okay? For electric current to flow through a liquid, there's got to be ions. There's got to be atoms with a charge, okay? These are just molecules. They don't have a charge on them for electrons to travel through, okay? When the electricity comes in here, it's going to hit this molecule and it's going to say, there's nowhere for me to go. There's no charges in this molecule for me to travel through. But say there's something like salt water, right? It's got a bunch of ions in there. It's got some positive ions, it's got some negative ions. That electricity could bounce from each of those ions and get to you and then shock you, okay? So a strong electrolyte is something with a bunch of ions in it. A weak electrolyte is something that doesn't have a lot of ions in it, okay? With Gatorade, when they say, oh, it's got electrolytes, it's got salt in it. That's what all that is, okay? If you look at Powerade, it says all these ions. It says I got 4 different types of electrolytes in it. What Powerade has is it has calcium in there, okay? It's got some salt in there, okay? It's got a little bit of potassium, I believe. And I believe the last one it has in there, if I remember correctly, I believe it's got magnesium in there as well. Yes, it's got magnesium. So those are the ions that they put in there. It's just different types of salt, okay? That's all Gatorade is that it's Kool-Aid with salt in it, okay? You need these ions in your body for your muscles to react, right? Your muscles flexing is just an electrical current going through them. If you don't have these ions, your muscles can't flex and they start to cramp up, right? They can't relax. They just feel like, I need to be 10-step all the time. I have no ions, right? But when you drink Gatorade, it gives you those ions, able to conduct that electricity smoothly. You don't have any buildups, okay? Everything is functioning properly. So, strong electrolyte, something where stuff dissolves a lot and creates ions, okay? Weak electrolyte, something where something doesn't dissolve, right? If I put a rock in water, that's not going to be a good electrolyte because it won't dissolve. What we need to know for this, we need to know our solubility ions, we need to know our strong acids and our strong bases, okay? Because those are things that create strong electrolytes. Again, strong electrolytes are things that dissolve. So, you need to know those 4 solubility ions, NAC, no, okay? Alright, so this is NAC, no. These are the things that, sorry, this was NH4, I was wrong. These, anytime you see a compound with these ions, they're automatically going to dissolve. So, if I see NaNO3, and you're wondering, is this going to be an aqueous compound or a solid? You're going to say, hey, it's aqueous because it's got one of those, in this case it's got 2 of those solubility ions, so it's going to break apart and dissolve and be a strong electrolyte, okay? What if I got something like KCl? Is that going to dissolve and be aqueous? Yes, it's got K in it, okay? It is aqueous. It's got that K in it. It's going to dissolve. It's going to be a strong electrolyte. What about when I combine those 2 liquids? When I combined them, it created potassium nitrate and lead iodide, okay? Potassium nitrate, it's aqueous because it's got one of those solubility ions in there, but lead iodide, it doesn't have either of those solubility ions in there, so it's not going to be aqueous, it's going to be a solid, okay? It's going to be a solid. So, know those solubility ions. If you don't see those in a compound, you know it's aqueous, it breaks apart, it's a strong electrolyte. If you don't see it, okay, that means it's a solid, that means it's not going to be a good electrolyte. And then we got to know those strong acids and those strong bases. Those strong acids and strong bases are strong electrolytes. They dissociate a lot, they break apart, they dissolve. Okay, that's why they're strong. When you put acid on your skin, the reason why it reacts with your skin is because that acid will break up into ions and they're ready to react with anything. So you got to know those strong acids and our strong bases. Okay? Strong acids aren't bad. You got HCl, HBr, and HI. Those are the 3 2-atom acids. And then you got HNO3, H2SO4, you got HClO4, and you got HClO3. Those are your strong acids. Those are guys that are going to dissociate, break apart every time they're ready to react react with anything. So these are strong electrolytes. They dissociate a lot. They conduct electricity. You also have your strong bases, which, if you look on the periodic table, LaIOH or LiOH, NaOH, KOH, RbOH, and CSOH. So if you look at the alkali metals, it's all those alkali metals except for hydrogen and francium, the one on the top and the one on the bottom. And then we go to alkaline earth metals, and there's only 3 elements that form bases there, and that's calcium hydroxide, strontium hydroxide, and barium hydroxide. Okay? So those are 3 guys that are lined up with the transition metals, okay? Calcium, strontium, and barium. Okay, they form the strong bases. So these guys are strong electrolytes. They're going to dissociate. Whenever you see these guys, they're going to be aqueous, right? They're going to have that parentheses with the aqueous there for them. So we need to know that NaCNO creates aqueous solutions, and the strong acids and strong bases create aqueous solutions. All right? So now, why do we need to know all this? Well, we need to know it for our net ionic equations. But first, let's do some naming between weak acids and strong acids, okay? Or figuring out if they're weak or strong. Here are some electrolytes. And I want you to tell me if they're strong or if they're weak based on our strong acids, strong bases, and our NaCNO, okay? I look at NaCl. Is that a strong electrolyte or a weak electrolyte? Well, I look at it. Does it have any of those solubility ions? Yeah, it's got Na. So it's aqueous, it'll break apart, so it is a strong electrolyte. What about NH42SO4? Okay, it's got NH4 in it, which is one of our solubility ions, right? No, so that is strong. HCN, okay? Hey, it's got an H in front of it. That means it's an acid. Is it one of our strong acids? No, it's a weak acid. HCN isn't a strong acid, it's a weak acid, so it is a weak electrolyte. C6H12O6, does it have NaCNO in it? No. Is it a strong acid or is it a strong base? No, so it must be weak. Okay, must be weak. So, again, we need to know these things for our net ionic equations. All right, so let's talk about net ionic equations. What are they? Okay, what are net ionic equations? These are just equations where we only write the chemical equation for, I should say, for substances that aren't spectator ions. Okay, so they're pretty much just equations that show the ions that get to work in the reaction, right? There are some spectator ions that just deliver other chemicals into the solution. So net ionic equations only focus on what is involved in the reaction, okay? So let's go ahead and go through this. Let's look at a simple one of lead nitrate and sodium bromide. So what we do with these net ionic equations is first we got to identify what's aqueous and what is solid, okay? Or what's a strong acid, what's a weak acid. I look at this lead nitrate, right? It's got a missing state. I look at lead nitrate and I think, does this dissociate? Does it have NaCNO in it? Yes, it's got NO3, right? So this is going to be aqueous. NaBr, I think, does it have NaCNO or is it a strong acid or strong base? It's got Na in it, so it's aqueous, AQ. It's got our NaCNO. PbBr2, okay? Does this have NaCNO in it? No. Is it a strong acid or is it a strong base? No. I'm going to say that this is a solid. And then NaNO3, does it have NaCNO in it? Yeah, it's got Na and NO3 in it, so it's aqueous. Okay? Now, what we do is we separate everything that likes to dissociate. So we separate anything that has NaCNO in it, and we separate anything that's a strong acid or a strong base. So let's go ahead and do that and separate these guys into their ions. Okay, now this is tedious, but you have to be clear and concise with these. Okay, so when this guy splits up, it's going to split up into lead and nitrate. You have to list the charges. You have to list how many of each ion there are, and you have to list the state of each ion. So the charge on lead is 2+, nitrate is -1. I only had one lead here, but I had 2 nitrates here. Okay? Lead is aqueous because it came from an aqueous solution, and nitrate is aqueous because it came from an aqueous solution. Okay? First one done. NaBr. It's an aqueous solution, right? So it splits apart, or it's got NaCNO in it, I should say, and it's got, or it's a strong acid or strong base, so it breaks apart. It's going to break up into Na plus aqueous and Br minus aqueous. And since there was a 2 in front, I got 2 of each. Okay? PbBr2, that's a nice one. Okay? It doesn't break apart because it was a solid, right? It's not a strong acid, and it doesn't have NaCNO in it, or it's not a strong base, so it just stays together. Okay? And then another strong electrolyte that breaks apart, I'm going to have 2 NAs, aqueous with a +1 charge, and 2 NO3 negative aqueous. Okay, so this is called the complete ionic equation. This involves everything, not just spectator ions, or it includes the spectator ions and things that created that precipitate or that solid. So I'm looking at this, okay, this is the complete ionic equation, okay? To get the net ionic equation, we just cross out things that are the same on both sides. I got 2 NO3s over here, I got 2 NO3s over here. I got 2 NAs over here, I got 2 NAs over here, and that looks like things that are exactly the same on both sides. Yeah, there's a PB over here and a PB over here, but they're not the exact same, right? It's not PB2 plus and PB2 plus, it's PB2 plus and PbBr. So then whatever I'm left with is my net ionic equation. So it's Pb2 plus AQ plus 2Br minus AQ goes to PbBr solid. And that is my net ionic equation. It only involves the stuff that made a solid, or it got rid of the spectator ions, okay? So my spectator ions were nitrate and Na. They just delivered other chemicals into there. They helped us get the Br in there and the Pb in there so that they could react to form that solid. Okay, so we just call these guys spectator ions because they didn't react. They didn't do anything. They were just a delivery system for our other ions, right? So you might remember this from last year and you're like, why don't you just say split apart the aqueous, keep the solid together? There's some other instances here where we step it up a notch where that's not always the case. All right, so let's say we got HF, AQ. It's going to react, let's say, with lead nitrate, and it will form nitric acid and lead chloride, okay? I'm not going to put an aqueous there. I want you to figure that out on your own, and then I will balance this, okay? So again, I like to list things as aqueous or not, or as a solid, okay, or a liquid or gas. We have no liquids or gas here. The only time you'll see those is when you see something like H2O, which we know is a liquid, or CO2, which we know is a gas, okay? So let's go ahead. I'm going to leave HF for the end, okay, and I'll explain that later. But let's look at things that we know are either strong acids or have NaCNO in them, okay? PbNO3, does it have NaCNO in it? Yeah, it's got NO3, so it's aqueous, okay? HNO3, it's a strong acid and it's got NO3 in it, so it definitely is aqueous. Lead fluoride, is that aqueous? No, it doesn't have NaCNO in it. Doesn't have a strong acid or a strong base, so it's a solid. And then HF, that is a weird one, okay? Because it doesn't have NaCNO in it. It's not a strong acid, but it is a weak acid, okay? So it won't dissociate because it's a weak acid, but it's still aqueous, okay? So here's where things get tricky, all right? The only thing I want you to focus on is that we split up everything with NaCNO and we split up everything with a strong acid, a strong base. Anything else, we keep together. Okay, so what you're going to see is you're going to see a lot of weak acids, which are just things that start with H that aren't our normal strong acids, or anything that ends in OH that isn't a normal strong base. Okay, so those guys aren't going to separate. Weak acids and weak bases aren't going to separate, and then anything that's a solid isn't going to separate. So in this situation, we have two compounds that aren't going to separate. We have two that will separate due to NaCNO and being a strong acid, but the other ones aren't because they're a weak acid and a solid. Okay, so let's get to that. Again, this is aqueous, right? And you're saying, oh, we split up things that are aqueous. That's why we're forgetting this rule, because we're not going to split this guy up because he's a weak acid. He doesn't dissociate. Weak acids don't dissociate. That's why they don't eat your skin. Okay, strong acids do dissociate. That's why they do eat your skin. They're ready to react. So this guy's going to stay together. 2HF aqueous. Again, we don't split up weak acids or weak bases, and we don't split up solids. This guy, he's got NaCNO in him, so we're definitely going to split him up. Pb2 plus AQ, 2NO3, AQ. Weak acid, or strong acid, sorry, so we're definitely going to split that up. 2H plus, AQ, 2NO3, AQ, minus, and then PbF2, it's a solid, so we don't split it up. Again, that's our complete ionic equation, and then we cross out things that are the same on both sides. So, the only thing that's the same on both sides here is 2NO3. So that was our spectator ion. We just had one this time. So now we just combine things that we have left. And these are the things that created something that reacted, right? HF, right? It didn't break apart that much, okay, because it's a weak acid. The lead helped us make the lead fluoride, and the H plus came from the HF, right? It's still there, okay? And the F from the hydrofluoric acid helped make the PbF2. Again, HF is a weak acid. It doesn't really dissociate a whole lot. It does dissociate a little enough to create some PbF2, okay? So remember, net ionic equations. Don't dissociate weak acids and weak bases. Don't dissociate solids, okay? And the way we know they're weak acids or weak bases is if they start with H and they're not one of our strong acids, or if they end in OH and they're not one of our strong bases, okay? So that's the thing that we've added this year, okay? That's why we need to know NaCNO. That's why we need to know our strong acids and our strong bases. Sulfuric acid, calcium hydroxide, they're going to make water and calcium sulfate. All right, guys. So, actually, let me switch this up. Let me switch this up real quick. Let's make this HNO3, and let's make this NO3 too. Okay, let's do that one. All right. So in this situation, we got a strong acid, okay? So it's going to be aqueous and it's going to dissociate. So I'll just dissociate it now. Let me balance this correctly. Okay. So let me just dissociate this now. 2H plus AQ and 2NO3 minus AQ. Calcium hydroxide, strong acid or strong base or NaCNO? Yep, it's a strong base. Okay, so it's going to be split up into calcium 2 plus aqueous and 2OH minus aqueous. Again, make sure you have your charges and your state, okay, right here so that it counts, all right, or else they won't give it to you. H2O, what is that? Okay, it is a liquid, okay. Is it a strong acid or a strong base? Nope. Does it have NaCNO in it? Nope. We're going to keep it as 2H2O. Keep it together. Then calcium nitrate, strong acid, strong base? No. Does it have NaCNO in it? Yep, it's got NO3. So it'll be Ca2 plus AQ and 2NO3 minus AQ. Right? Cross out things that are the same on both sides. And we are left with 2H plus AQ plus 2OH minus AQ and 2H2O liquid, which when we reduce, we just get rid of those 2's. Right? So that's our net ionic equation. And here's the trick, guys. This was a strong acid, right? This was a strong base. Whenever it's a strong acid, strong base reaction, this is always going to be your net ionic equation. Okay? Always going to be your net ionic equation. Whenever you see a strong acid, strong base, H plus plus OH minus equals H2O is always your net ionic equation. Alright? So fun fact, if you see a strong acid, strong base and it says what's the net ionic equation, just put that down. Okay, so I go ahead and I look at these. I see radium hydroxide. Is that a strong acid or a strong base or have NaCNO? No. Okay, it is aqueous because it's not a solid. Okay, it's a weak acid and weak base. We always assume they're aqueous, but it's not going to split up. All right, because it's a weak base. Yeah, always assume weak acids and weak bases are aqueous. They just don't split up. HCl. Hey, that's a strong acid. That'll split up. H2O, remember that's a liquid, right? It's got no NaCNO, it's not a strong acid or a strong base. It's just a liquid, so it'll stay as is. And then radium chloride, NaCNO, no. Strong acid, strong base, no. So it must be a solid as well. So it stays together. Oh, I forgot to balance this guy. It's never too late, right? We got 2 here, put a 2 there, and 2 in front of each of those ions. Sorry, guys. So I look at this and I say, okay, there's definitely a lot we didn't separate, but that hydrochloric acid separated. Is there anything I could cross out here? Nope. So this is my net ionic equation. Okay? So the biggest thing from today, okay? Separate anything with NaCNO and anything that's a strong acid or a strong base. Don't separate solids, okay, anything without NaCNO in it, and don't separate weak acids or weak bases. Okay, and remember, we know if it's a weak acid or a weak base, if it begins with a H and it's not in our strong acids, it's a weak acid. If it ends in OH and it's not in our strong bases, it's a weak base. Alright, so that's it for today. Sorry this video was so long. I kept it under 30 minutes though, which is pretty good. Have yourselves a great day.